All right, great. Yeah, thanks for the intro, Charlie. And actually, we won't just be talking about vector search. We'll be talking about a new area I'd like to introduce you folks to, but we'll get to that in a second. So let me get to the next slide. Okay, so I'm gonna give a quick outline of the talk and a justification for giving it. So I want to start talking about the challenges of building a semantic product search engine. Then I'll get on to the bulk of the talk, which will talk about NOLIR, otherwise known as vector search, semantic search, whatever you want to call it. Then I'll go on to briefly talk about this new area that I've come across called extreme multi-label classification and how that can be applied to search when you have sufficient training data. It's a very different approach to some of the other ideas you'll have seen. And that's very interesting. And then finally, I'll cover a system architecture for combining these different types of approaches along with BM25 into to produce this sort of best-in-class retrieval engine. Okay, so a number of you work in e-commerce. Obviously, not all of you work in e-commerce, but I wanted to sort of cover some of the unique challenges we face in building a product search engine that searches for products. The biggest challenge is probably the wide variety of query types. So people can enter dimensional queries, SKU numbers, non-product queries, as well as your usual sort of DEWALT drill or looking for a lawnmower or something. So we need a search engine that ideally can handle these wide variety of different searches, as well as solve the traditional problems such as typos, foreign language queries, and all those other things that you'll find in a regular search engine. We also have a lot of colloquial terms such as industry jargon, and we need to handle things like SKU variants and out of stock as well. So what most of you will be familiar with is typically in most sites, and this is not just for e-commerce, if you look at your queries and how commonly they are executed in your query logs, you'll follow that they follow a zip theme distribution. This is very common in natural language types of problems, as well as lots of other areas such as graphs and edges within graphs and so on. What this means is you have a small number of queries that constitute most of the query volume. And those are actually some of the easier ones to handle. It's really what we call the tail and long tail queries that pose most of the problems. So we have a large number of unique queries that are executed very rarely that form this sort of long tail of the distribution to the right. And that's really where you'll find the most advantages from having a semantic search engine of any type, not just for product searches. Why? Because that kind of engine can handle things like synonyms and typos and the wide variety of different terms that people enter in the query that produce the vocab mismatch problem between that and what is in the catalog. So if you're looking to build a semantic search engine, what I would suggest is that you think about how you want to apply it and where you want to apply it. And the biggest gains you will get will be in the tail. Google is kind of well known for first trying some kind of vector search approaches on the very hard to match tail queries in their search logs before they started to apply it to the rest of the stack. So this doesn't just apply to product search, this really applies to most search problems. A brief history of information retrieval. I'm sure most of you have a pretty good idea of this, so I won't spend long on it. So back in the 60s, we had sort of basic text search. This is like Boolean retrieval and some regexes, some very basic stuff. And then the vector space model came along, which is really kind of inspired by probabilistic IR. And a lot of people realize that so TF-IDF can be phrased as a sort of relaxation of the probabilistic IR model. That's covered in the Stanford book on information retrieval, if you're curious about that. And people started doing simple things like stop words and stemming and so on. Then into the early 2000s, we started to see machine learning become increasingly used within the search domain for learning to rank for conceptual search using LSA and LSI and LDA and things like that. And the increasing use of sort of NLP approaches like NER, name entity recognition, and so on, coming into the play and sort of helping to improve the relevancy of the search stack. The thing you'll note there is with that second phase, that's when the inverted index came into play, and everything was very reliant on having this inverted index structure in place to do the token matching. Then around the late 2010s and beyond, we start to see companies like Google with Hummingbird move towards more of a neural search or a vector search model, where they're starting to bring deep learning models into play. One thing I'd like to cover today is also a new area called extreme multi-label classification. I don't think this will be a paradigm shift like some of these other approaches. I think it will just augment some of the existing approaches that we already have, but it can provide another way to get really relevant results when you have a large volume of training data. And one that I haven't seen much talked about in industry, so I'd like to bring your attention to it today. So to sort of highlight the rising popularity of neural IR, there's this nice chart published by Bhaskar Mitra, who is a renowned researcher at Microsoft who's working on neural information retrieval. He's just shown the percentage of papers at SIG-IR that are published every year on neural IR. So you can see as the deep learning revolution took off, more and more people publishing more and more papers using deep learning for search, which is probably not a surprise to most people. So before I get into the specifics of how you might build a vector search engine, I just want to clarify sort of how we generally approach search, both traditionally and also with machine learning, just to sort of outline the parallels there. So in traditional sort of BM25 search, if you say using just plain Solr or Elastic or something Lucene-based, that gets executed in kind of a two-step process. First, you enter the query, and Boolean retrieval happens, right? You're looking at you're running kind of a bitwise operation to get binary matches against the keywords in the documents and to produce an initial matching set. Then sort of Elastic will then bring in the sort of ranking logic into play using TF-IDF or BM25, which is a variant of that, along with any other kind of custom boosting or weighting that you have to help re-rank that initial matching set of documents so that the most relevant documents are put on top. So even in Solr, we have this sort of retrieval step and then this sort of re-ranking step. It's not doing LTR out of the box, but that TF-IDF ranking is still kind of a re-ranking phase over the Boolean retrieval set, at least as I think about it. When we approach semantic search from a machine learning perspective, we actually follow the same kind of paradigm in general. We'll have one or more retrieval models that produce an initial matching set. You can think of those models kind of like classifiers, where they're really trying to say, within this large set of documents, which of them are relevant to the query. And here we're really optimizing for recall, i.e. reducing false negatives. And then we'll have a re-ranking step where we'll take that matching set and use machine learning algorithms to re-rank the results by relevancy. So this kind we'll use LTR models, neural ranking models, or something like that. So it really follows the same paradigm, but the way in which we do it is very different. Also in this retrieval step, we start to leverage things like k-nearest neighbor search and approximate k-nearest neighbor search algorithms to scale out the matching to a large corpus of documents, as we can no longer use an inverted index in most cases, as we're working with vectors and not tokens. So for the rest of this talk, I'll focus mainly on models for matching or retrieval, which is really where the semantic search tends to happen primarily, and where you get the most benefit in terms of improving recall, more so than improving precision. Although there's certainly use cases for using neural models in re-ranking as well. So, so when we think about using neural models for information retrieval, what we're really trying to do is build a model for metric learning. And that's kind of a phrase that was really saying we're trying to learn a similarity between a query and the document. This often takes the form of what's also called embedding-based retrieval, or EBR, where a vector is generated for the query and then matched against a set of vectors that have been pre-calculated for the product set or the document set. And what we were trying to do is we were trying to train a model to maximize the similarity between queries and purchase products or clicked documents, and then minimize the similarity between queries and irrelevant documents. So this diagram on the left kind of tries to illustrate that, where we have a query text and document text. Then we have encoders that take in the query representation and document representation. We generate vectors for each of those two, and then we have a layer at the top where we're trying to push similar products and queries together and trying to separate irrelevant documents from the queries. And then retrieval is then done using proximate k-nearest neighbor search, using specialized algorithms such as HNSW or SCAN to speed up the k-nearest neighbor retrieval performance from linear to sublinear time. As when you have a very large corpus that you're matching against, say in the order of millions, doing brute force KNN is usually way too slow. Okay, so if you're building a neural IR model, the first thing we need to think about is how we tokenize this text as we're going into the model. So you might be surprised to learn that actually traditional approaches are still pretty common in this space, where you can use unigram and bigram tokens and character trigrams to get subword tokens, apply that over the text coming in, and then use that as an input to the embedding layer going into the encoder. This is more commonly used in simpler neural models, such as where we have an average embedding model or something like a feed-forward model, such as DSSM, which I'll get to in a second. What is becoming increasingly popular, at least in other areas of NLP, is you'll see these sort of trainable tokenizers, where you actually have a model that learns how best to tokenize your text. This has been very popular in machine translation, and it's now being used in language models, and thus also in some search engines that use neural IR. The idea there is to use compression algorithms such as byte pair encoding to try to figure out the optimal way to segment a string so it can be compressed in an optimal way. What this often results in is that you'll have substrings within a term that vary in length based on how common that character sequence is. So if you have a word and it has a very common character subsequence, then that will get a much longer token than rarer character sequences, which will get much smaller tokens. And that's how the compression algorithm works. And that gives a very good representation for these more powerful models, such as transformer models, to get a representation over the text. So both of those approaches use what I would call subword tokenization, where you're looking at not just the words themselves, but parts of the words in order to do the matching. In the first approach, we have character trigrams. So we're just taking a 3-character letter window over the word and getting lots of little pieces out of the 3-character sequences. With the subword tokenization models, such as BPE, we're actually using a sort of a model to derive those subword tokens. And using those subword tokenization approaches that can help us make the model more robust to typos and other kinds of noise that gets into the queries. So one thing that we need to consider building a neural IR model is how to handle very rare and out of vocabulary tokens. So as we have a model that's trained purely on the training data, the only words it will understand a priori are the words it sees in the training data. If you have a term that's never occurred in the training data, out of the box, the model will not know what to do with it. Some sources of out of vocabulary tokens are sort of typos and query terms that are not in the training data, and so very long tail queries where you have terms that are just very rare or have not been seen before. Some solutions to this are first the subword tokenization that I just mentioned, where if you have word parts that have a semantic meaning in and of themselves, they can be used to get matches on the subword parts to help sort of match against these tokens that you haven't seen, provided there are parts of those tokens that look relevant. Somewhat dependent on those subword parts having some semantic meaning. You can kind of think of this as a bit like stemming in a sense, or lemmatization, in that even if you have a large number of variety of word forms, if there's some root there within the word that has a common meaning, then you can match against it. However, this doesn't work well for proper nouns and industry jargon, where the subword parts have no special meaning when you take them within that term. Another approach is hashing. So you can take each out of vocabulary token and hash it to a unique hash bucket, and then you can learn vector embeddings for those hash buckets. That sounds like it would not work well, but there's a couple of papers that have shown that it does look like a promising approach. two matching, so out of vocabulary tokens. However, hash collisions can result in false positive matches, as you would assume. Okay, so I'd like to talk now about common architectures for neural information retrieval models. So the most common architecture that you'll see is this sort of Siamese neural network. This is kind of one of the first approaches that people use to train a neural IR model for retrieval. And the idea here is that you have an encoder that operates over a piece of text. So the example on the right here is actually shown from one of our recommendation modules at Home Depot. The details can be found in that paper referenced at the bottom from Rexis. And the idea is that you have, here you have a title and description for a product, and we wanted to basically train a model to match products with similar content and not to match products with different content. And we'll use user behavioral data to determine what is similar and what is not. So the title and text kind of come in at the bottom of the neural network. They get tokenized and then passed into an embedding layer. Excuse me. And then a bidirectional LSTM takes those embeddings and generates a vector encoding. And then we try to maximize the cosine similarity between two vectors. So what you see here is you have these sort of two pieces, which is why it's called a Siamese network, where you have the same encoder on the left and the same encoder on the right, and those shared parameters are exactly the same neural network. And what they're doing is trying to learn a very good representation of the text in a vector form, such that similar products have similar vectors with a high cosine similarity, and dissimilar products have a dissimilar vectors with a low cosine similarity. And you can train a model to do that if you give it a large enough trained data set. And you can imagine this can then be applied also to queries and documents, where you have a query coming in on the left-hand side and a document on the right, and you have the Siamese network trying to match the query and the document embeddings to one another. So again, that's called a Siamese network because you have that sharing of parameters and structure between the two sides. So that was kind of one of the first approaches to doing sort of neural IR models. And one of the first papers to try this was the DSSM model from Microsoft in 2013, the Deep Structured Semantic model. This is an early Siamese network, and you can see it's not too apparent from this picture here, but you can see you have these towers here that are basically the same network structure that's just shared between the query and the document. So on the left, you have the query coming in, getting 128 element vector encoding from the encoder. And then each document also gets the same 128 element encoding. And then we're trying to run a cosine similarity between the queries and the documents using those vectors to do the matching. So later you start to see people start to use what are called two Teranormal networks. So the idea here is very similar to what I just showed you, except they remove the constraint that both encoders have to be the same model. So it allows you to then have a different set of features and a different way of embedding in a document versus a query or a user. The example here is actually from a recommendation model, but the idea is the same. So you see here you have on the left, you have user features, context features, and app features going into these two regular layers. And that forms a sort of the one tower of the encoder. And then on the right, we have features from the app going through a different set of encoder to get an app embedding. And the problem they're trying to solve here is Google Play app recommendation. Again, the idea at the top here is that you have a dot product you're trying to maximize and train that with sort of cross entropy loss. So the takeaway here is that you can have the Siamese network type of architecture, but you don't have to have the same encoder on both sides. You can have different encoders that can take in different features that are relevant to your problem. For example, in the search space, your product encoder may have a lot more features that you have from the product catalog that you don't have from the query. For instance. And also, it's quite common to have user-specific features also coming into the query encoder for some of these models. To see some examples, there's a JD.com paper on e-commerce there that also kind of uses this type of architecture. So the next question is, well, how do you get training data to train these models from your site data? So obviously, like in most problems, we want to use the clickstream to try to generate signals to train our models. To use positive signals, you may use purchases or clicks, and then for negative signals, it's common to use sort of randomly sampled docs and documents that the user has sort of skipped over on impressed but not clicked, for example. The research argues that some random negatives are needed to differentiate what we call the hard negative cases that are close to the query from the majority of documents that do not match the query. So there's sort of active research in the area onto how to mine negatives effectively from the data. And the performance of your model will depend very much on how well you mine these negatives. These negative examples. The positive examples are usually easier ones to pick. It's really how you pick the negative examples that can really make or break a given model. So we can differentiate between hard negatives and soft negatives and easy negatives, I guess, here. So an easy negative example for a query will be a random document that has no customer interaction data for a given query. Hard negative would, in contrast, be something that looks very much like a relevant document, except for a few things that would make it irrelevant, a few terms here that may produce a negative match. And determining those hard negative examples is really key to building a good neural retrieval model. So it's important that you sort of pick hard negatives carefully. So for example, if our query is chordless circular store, note the chordless part. A bad hard negative will be circular store without a chord because that is relevant, and thus a bad hard negative because it's actually a positive example. Whereas chorded circular store would be a good hard negative because it looks very similar to the query, but they're actually asking for something without a chord, not with a chord. So it's very close in semantic space to the query, yet still being irrelevant to the user. And that is an example of a good hard negative. There's various ways you can mine those from your data and from the model itself. The approaches discussed in the literature tend to use the model to mine those hard negatives in kind of an active learning type of scenario, where you're asking the model for which negative examples do I have that are sort of closest in the similarity space to the query. And so people can do what's called local negative mining using the mini batch, just to mine within the mini batch while training the model and find the closest matching negative within the batch. Or you can do it globally, and every epoch the model is trained, build some kind of inverted index, or sorry, continuous neighbor index structure over the data and try to mine the negatives from the data before the model is trained over the next epoch, finding those negative examples that are closest to the query while still being negative. So at this juncture, I want to make a distinction between the two types of models I see in the literature, what I would call content-based models and behavioral models. So the kind of approaches I've shown you, I would call content-based models, in that they use tokens from a document to learn a semantic representation of the document based on their textual content. And that represents the more common route to building these types of models. The advantages of that is that any product can be matched in your catalog, including those with little to no user behavior data interactions, because all you need is a textual representation. And this is true for recommendations as well as search. The second type, which is less commonly discussed, I would call behavioral models. And this is kind of a different formulation of the information retrieval problem, treating it as a classification problem. So given a query, can we predict the products purchased, where the products can be viewed as labels in a very large kind of label space, just like you would train a machine learning classifier in a more traditional context. To train these models well, they need a large amount of user behavior data, and they rely on that rather than content. And just to clarify, both of these models are machine learning models that are trained on typically on implicit signals derived from a clickstream, rather than some other approach. So with that in mind, I'd like to talk a little bit about this sort of classification approaches. So one area that has started to get researched very recently, as of this year, into solving semantic search is this idea of extreme multi-label classification. So the idea here is you have a set of points, which for our use case will be queries, which is typically a very large space of input data or queries, and we want to match those against a very large space of labels. So this unpacking the terms here, the extreme part means we're doing multi-label classification in the sort of extreme setting, because the number of labels we have is not tens of labels or hundreds of labels. In some cases, it's millions of labels that we're trying to predict. And it's multi-label classification because for a given query, let's say we want to predict all of the documents that are relevant to that query. So each of those documents can be considered a label. So we're trying to do at scale, in the extreme case, multi-label classification of a very large label space. The image here is taken from the Galaxy paper, which is referenced at the bottom. So earlier this year at KDD, Amazon presented a paper called Semantic Extreme Multi-Label Learning for Semantic Matching in Product Search. And the sort of overview of the model is kind of illustrated on the right where it has this sort of tree structure. So as part of the paper, Amazon defined this framework they call the Picos framework, which is prediction in enormous correlated output spaces, a bit of a mouthful. But the key idea of this paper, and this is kind of building on other research in this extreme multi-label classification space, is that we can basically take the documents, cluster them together to form this sort of tree structure, and then train a series of classifiers to navigate this tree structure and go from the query to the clicked documents by navigating that space. So they have three kind of steps into building this model. First is an indexing step. So we take the products and they cluster them based on the query terms and the document content they contain using hierarchical k-means clustering. And that gives you what they call a label tree, which is you'll see in the image on the right. The label tree is really just a hierarchical tree structure that has at leaf nodes all of the documents in your retrieval set that you would want to match against. Once they have that structure, then they train a series of binary classifiers to route a query, which will come in on top of the tree, all the way to the leaf nodes that will match that query. So to do that, each non-terminal node in the tree, including the root node, has a classifier in place that is trained to determine which of the paths down the tree the query should be routed down in order to match the relevant documents in the trained data set. The classifiers take query features as inputs and use those features to sort of route themselves down the tree. And then once those classifiers are trained at inference time, a beam search is used to take a query and basically navigate the label tree and determine a set of matching leaf nodes. A beam search, if you're not aware, is a sort of search algorithm that keeps a number of candidates in memory at a time, so it allows it to sort of efficiently search through a kind of large and branching search space without having to do a lot of backtracking, which would be inefficient in this scenario. Then finally, it has a matching set of documents, each of which have what is similar to a probability score associated with them based on the classifier's confidence at each level of the tree. And then the most relevant documents are those then that have the highest classification score according to the models within the tree. So this image is taken from the Amazon blog. You can see the GIF is sort of animated. It tries to sort of illustrate the beam search process. As the input or query comes in, multiple nodes are matched and kept in the beam search memory. And then it sort of traverses down the tree to try and find what are the most relevant documents at the leaf nodes that match that query. It's worth stating that this type of problem, this extreme multi-label classification problem, originated in sort of searchio kind of problems where they were trying to take a document and predict the top keywords to index for that document and sell as sort of head terms in an SEO kind of approach. So in that case, the labels are the terms in the document. As you can imagine, that's a very, very large label space. Here, Amazon is figuring out that, well, maybe we can do the opposite. Maybe if we're going to a document to the most relevant keywords, maybe we can go from a set of keywords to the most relevant documents. And this, according to the paper, this works surprisingly well for them in the context of the product search problem. So in summary, the model learns an indexing structure using hierarchical k-means clustering, similar to that used to solve some approximate k-nearest neighbor search problems. Some of you may recall my talk from 2 years ago at Haystack, where I described hierarchical k-means as one approach that people use to build an ANN index for doing fast nearest neighbor search. So one way to think about this model is it's a model that kind of learns that index structure in a way that also allows it to provide relevant products without needing any kind of external indexing structure to support the model. As such, the inference time is extremely fast. Amazon claims it's about 1.25 milliseconds for millions and millions of products in their catalog. The training time for this type of model is 6 times faster than the best neural model, which is a convolutional DSSM model, which is a variant of the DSSM model I showed you guys earlier that has a convolution over the terms. And the recall at 10, which is their performance metric, the relevancy metric, was twice their best neural model without using a neural network to serve this kind of search. So bear in mind that this is one of many extreme multi-label learning methods, and it's just the first that's really been trying to apply directly to search. I encourage you to sort of look at the repository below in this slot to see some of the large body of work that's gone on in this area in the last few years. It's a very kind of actively researched area, and there's many applications of this type of approach that is applicable to search domain and recommendations as well. Microsoft, for instance, has been a very active researcher in this area and has 2 of the leading models in this domain, Slice and Parabol, and there's a bunch of other models that are also very effective and have open source implementations. Not all of these models are tree-based. Some actually use approximate nearest neighbor algorithms, such as HNSW, to do the initial matching phase and then train a series of rankers on that matching set. So they do not all follow this sort of tree structure, although that is the most common design. Okay, so finally, I wanted to briefly discuss how you would combine these different approaches in a final sort of best-in-class retrieval system. As there are advantages and disadvantages of these kind of classification type approaches, as well as the neural IR approaches, as well as obviously more traditional models like BM25. So one architecture Amazon proposed in that paper is shown on this screen here. So you'll see what they're proposing is having multiple retrieval models in this sort of gray box here. So we have a lexical matching, which is just basically BM25 or some variant of that. And then you have these 2 semantic matching models. So they're using their embedding-based neural retrieval model, such as DSSM, and they have this extreme multi-label learning model, such as the Picos model I just showed you. All 3 of those models generate a set of matching documents for a given query, and those get merged together into this matching set and deduplicated. Those then get passed on to this ranking layer. Amazon is not the only company to propose this sort of ensembling type approach to machine learning retrieval. For instance, here's another example from Taobao, who are Alibaba, in their paper Embedding-Based Product Retrieval in Taobao search, where they use lexical matching, embedding-based retrieval, and a collaborative filtering model to produce the matching set. So you see that is, again, the retrieval set of algorithms. So they have 3 different retrieval systems. They deduplicate excuse me, they deduplicate that set of documents and merge them together in the second step to produce a matching set, just like in the last PowerPoint. And then finally, they pass those to the ranking layer. And they have 5 different ranking approaches there that they bring to bear on a problem. So although this looks a little different, the core idea is the same. You have multiple retrieval models producing a single deduplicated matching set that then goes through a series of rankers before being presented to the customer. Right, so that hopefully wraps up the talk there. And I would like to open the floor for any questions you may have.
Simon, thank you so much. So, well, that was a lot of information there. Let's see if we have some questions from the floor while Simon has a quick drink there to refresh his tired throat. Right, let's have a look. We have Scott's got a question. What are the differences between extreme multi-label learning and term co-occurrence boosting strategies?
So, I mean, term co-occurrence, you're still learning information matching between the terms. The extreme multi-label learning is really, it's almost like a recommender system in some ways. Like it's really just routing a query directly to the documents that are most likely to be clicked for the query. So it's really a very different approach. You can use content to influence the structure of the tree, but it can work, at least according to the paper, without any kind of content at all. Although they don't advise that. They advise using a combination of the sort of query terms to cluster documents along with the content, which is a title and a taxonomy as well. So one thing I didn't really get into is how they represent the documents before they cluster them. So a big component of that is they take each document and they aggregate all of the query terms that have clicked on that document to perform that representation, and then they combine that with some content-based labels as well, and then do the clustering, and then they train the classifiers on top of the cluster tree, if that makes sense. But it's not really looking specifically at the content, and it only works, I think, based on having that large set of training data available to you. It's not going to give you a zero-shot retrieval, for instance.
Okay. Just quickly, do we have a question from the room? I guess
it looks like we don't.
Okay, so moving on back to Zoom. Deepak asks, with different retrieval models and merging, how do you drive facets?
That's a very good question. I can't speak to the literature here, and it's not something I've seen discussed an awful lot in the research. But I think that's a challenging area for sure. You could, for instance, rather than just relying on the inverted index, you could have your own models for doing that, let's say. Or you can, what is often the case is, you're not just using these models to produce all of the matching set, right? There's still usually an inverted index sitting there somewhere. What you're really trying to do is make sure the top set of documents, which needs to be quite large, are the most relevant to the user. But I don't think this is totally going to replace the inverted index, especially for scenarios like Fastly.
Okay, thank you. Erica Lunas asks, with vector retrieval, when or how do you know you need to retrain your subword tokenizer versus when to fine-tune the model?
I mean, I don't know if there's an obvious answer to that. It depends how often your data is changing and your catalog and your queries are changing. If your data is pretty static, then you're not going to need to change it very often. But you need to have an idea of how often your document set is changing and how often your users are changing the query set. The tokenizer itself is very fast to train, the subword tokenizers. It's a model that's going to take you a long time. So even on very large data sets, the BPE and the other variants of that are extremely fast to train. So it's more about when you want to train the model. One challenge is if you have this inverted index structure, right, built on top of your data, most solutions for that do not allow you to do incremental indexing or real-time updates. So if you want to add additional documents, you'd have to often need to reindex the entire catalog based on current open source solutions anyway.
Thank you. So John Kane asks, is BERT or other variants such as MBERT, are they required for semantic search? What would be the most effective out of all the other BERT variants?
No, I mean, you don't need to have a transformer or a BERT model to do semantic search. Some of the approaches don't use transformers at all. Like the DSSM approach is not a transformer, and that is purely trained from scratch on the trained data. One of the Amazon papers I referenced is the same. They don't use BERT, and they did a comparison with a transformer approach and this more simpler average embedding model, and they found that the transformer was not giving them any additional accuracy, and it wasn't worth the computational cost to try to scale it up. But it does depend on your use case. So some of it depends on how large your documents are. So if you need to index large documents and get information out of those, that's a lot more challenging area. Often in e-commerce space, and again, this Amazon paper talks of that, you can get pretty far by using the title and a few of the top key fields as your main sort of input to the model. But usually those models are also not deployed on their own. They're used in conjunction with BM25. So you can get matches on those larger fields as well from that.
Okay. I think Onkar hasn't had a question yet. What's the best approach to handle custom vocabulary with BERT and similar transformers?
Custom vocabulary.
Yeah.
Custom, so I guess the question is really, so you have a model like BERT that's been trained on a very large corpus, and then you want to apply it to some domain where you have a lot of custom tokens that probably don't exist in the original training data. So the traditional approach there is fine tuning. As those models are typically trained on a subword tokenizer, even without out of vocabulary tokens, you still have you'll still should be getting subword tokens that are in those terms. And so if you fine tune a model, it should in theory learn to make better representations of those new terms. Another approach in the Amazon paper, as I mentioned, is hashing. So you can try to use hashing to handle out of vocabulary terms, and then includes sort of domain specific terms. Okay.
And one last question before we close, and I'm sorry if you don't all get a chance to get your questions answered. I'm trying to give everyone a chance. So if you already had a question answered, I'm trying to give some new person a chance. Rennie Kriegler asks, what ways do you see to get some feedback from the models about the quality of the search results that be passed to the user? We know that's not exactly what you might be looking for, but you might be interested in these products.
Are you talking about sort of interpretability, or is that a question?
I think so. Yeah, explainability.
So the explainability, I mean, that can be a challenge with the normal models, as most people know, although there are ways to back into that. One way is you can look at the tokens, right, and you can see the scores against the tokens in the top matching documents and see how well those align. If it's an attention-based model like BERT, you can actually look at how the attention is, how the self-attention is working when it's encoding the document, and which parts of the document it's focusing on, and that can give you some idea. What you're not going to get easily is the type of interpretability you get from a Solr or Elasticsearch, where you can see exactly how the query is being parsed. That is always a pretty big challenge with these types of approaches. I don't think it's a solved problem yet. There's definitely work going on in that area. They can at least give you a similarity score. And unlike Solr or Elasticsearch, that is pretty well normalized, like it's on a scale of 0 to 1 if it's cosine, or minus 1 to 1. But presumably people want more than that. Another approach is just to look at the training data and try to see what that is telling the model for a given query, if you have the query in the training data that they're trying to match on.
Simon, thank you very much. Great to welcome you back to Haystack, and your talks are always fascinating and lots to unpack there. For those of you who didn't get a chance to ask a question, obviously Relevant Slack is the place to go, and Simon's a very active participant there. So thank you again, and I'm sure you'll be back again at Haystack.